Okay, let's move on. So we are not finished yet because this guy, 7 over 4, is fractional. So let's add two constraints, x1 less than or equal to 1 and x1 greater than or equal to 2. Graphically, this is x1 less than or equal to 1. You get, again, a fractional number, 7 over 2. But anyway, let's record the solution for a while and then try to see whether we need to move on. When you add another constraint x1 greater than or equal to 2, now the two constraints are basically conflicting with each other, and with other constraints you know this problem is infeasible, and then your node is dead again. Looking at your tree, now this has been done, this has been done, this has been done, and you get a fractional value here. Interestingly, you don't really need to branch on this node. Why? This is very important, so pay attention. We only have an alive node, which is node 6, with a fractional value here. However, we don't need to branch it because of what? Because that our z6 currently is 6.5. Okay, 13 over 2, 6.5. If we keep moving down by adding constraints, any IP solution that we can get, if there is any, cannot be better than 6.5. But our candidate solution is already 7. Okay? So it's impossible for us to keep moving down and get something better. So we can at this moment stop and conclude that this guy 2-1 is optimal. Okay? That's the part about bounding. Branch and bound is, you know what's branching, right? As long as you get a fractional value, you branch. And before you branch any node, you actually check the current value with the current candidate. And this allows us you bound yourself from solving too many nodes. Okay? This allows us to solve fewer subproblems and make the solution process faster. Okay. In summary, when we are running the branch and bound algorithm, we maintain a tree, right? Think about the case that you are actually writing a program to implement your branch and bound algorithm. Okay, then you are very close to really maintaining a tree. You probably don't need to do that, but you will maintain at least no loose leaves, right? So when you are solving this problem, your tree will become bigger and bigger, and then you branch, and bound. If a subproblem optimal solution is IP feasible, okay, that's great because we can get a candidate solution. We will immediately compare it with the currently best IP feasible solution. And in any case, we will stop branching this node. If the subproblem is infeasible, it's also great because we can stop branching this node. If its solution is not IP feasible, then either it is better than the current candidate, then we branch. Otherwise, we don't need to do that. Okay, so that's the general description of our branch and bound algorithm. You know how it works, you know why it works, and you will be able to use it. Very quickly, let me go over another example. This is our motivating example. Okay, two constraints, integer variables. Let's solve it with the branch and bound algorithm. First, you get this LR optimal solution. This is interesting because both variables are fractional. Now you need to decide which variable to branch on. Okay? For no reason, let me branch on x1. You probably want to think about whether it is any rule to choose a variable to branch on? This question is very similar to when you use a simplex method. If there are multiple variables that may enter, which one should you choose? Okay, here, if there are multiple variables that may be branched, which one should you choose? Okay, for no reason, let me choose x1. Immediately I get one part here, the other part here. The first node, x2, can be solved with integer solution 3, 3. So now I get a candidate solution. The second part can be solved, but x2 is fractional. So now I need to branch on x2, adding two constraints. One of them here is infeasible when I require x2 to be greater than or equal to 2. It's impossible. So this is infeasible, this node is dead. Here, this guy only give me such a tiny region here, but I can still solve and get an optimal solution. Unfortunately, x1 is fractional. Okay, then I probably want to keep splitting and get some other solutions. I check the objective value. Indeed, it's still possible to get something better. So let me do it. When I require x1 to be less than or equal to 4, the feasible region is just here. A solution for 1 is found. It's not as good as x2, so I will simply remove it. But this node is dead. And then x7 indeed is the best. So I update the current optimal solution to x7, and also this node is dead. Then I'm happy because everything has been done, and I found an optimal solution. x7, 5, 0. This is indeed optimal. Some remarks. When you need, sometimes you need to select a node to branch. If you think about the general branch and bound process, it's possible that there are many alive nodes, especially when you have many variables. Okay? Then there may be multiple ways of selecting a node to branch. One common approach is to branch the node with the currently highest objective value. Okay? You probably want to think about why. Why some people suggest to branch on the node with the highest objective value. It's related to the bonding process, related to bonding a node with the currently optimal solution. Okay? Another popular approach is that once a node is branched, all its descendants are branched before any non-descendant. Say it more informally. Once we branch a node, we keep moving down along this subtree instead of moving back and forth. Once we branch on here, we keep moving, and we never go outside this branch before we finish this part. Okay? Then you also want to consider why do we want to do that. And in fact, there are many other proposals for selecting a branch. You may even propose your own. But the fact is, there is no single best rule to branch a node. Okay? When you have multiple nodes to select, there is no single optimal way that is always the best. So it's case by case. Choosing a variable to branch on can also be a challenging task. Okay? If you read the textbook, there are some suggestions. Again, there is no single best way. So in some sense, you can just try to get lucky. The branch and bound algorithm guarantees to find an optimal solution if there is one. Unfortunately, it is an exponential time algorithm. Okay? You can feel that you need to solve many linear programs. Even though solving each linear program is easy, but there are too many to solve. And roughly speaking, when you have n integer variables, the time you need to solve the problem is approximately proportional to 2 to the power of n. Okay? That's why if we can accept that one variable is fractional, we leave it fractional. Okay, like those tables, chairs, or the number of personnel for United Airlines. Okay, when that kind of approximation is allowed, we set variables to be fractional. Otherwise, if you have, let's say, 50 or 100 integer variables, then you almost can guarantee yourself that your branch and bound algorithm will fail because you need too much time. Okay, so that's some general things we have for branch and bound. Okay, so that's the end of our introduction to branch and bound. As you can see, it just recursively solves many linear programs. For each linear program, you can have multiple ways to solve it, but at least you have your simplex method, right? So once you have your simplex method, once you know branch and bound, now you can solve any integer program if you have enough time. Okay, I'll probably stop here. In the next video, we will talk about another topic. It's about how to use integer or particularly binary variables to formulate some more problems. Thank you.